welcome to my presentation about Bayesian optimization for neural networks with small sample size data, a combined approach for feature selection and hyperparameter tuning. So I think the question that immediately arises is why should we look at neural networks and small sample size data, and why should we put emphasis on feature selection and neural networks? Well, let me motivate this question with the research project that I'm currently working on. In this research project, we are trying to forecast the revenue for the local transport company in Berlin, namely the BVG. And we've spoken to their forecasting experts and came up with a set of features. And we included all of these defined features into our LSTM with 2-layer, 32 units, nothing too fancy. And now let me show you how the training of this kind of like standard LSTM looks like. Here on the left, we see a very unstable training. We are starting with an already small loss, and we have a very high peak here at around epoch 500. So this is caused by high variance gradients, and they also lead to overfitting. Let me give you a numerical example to that. So in this validation set, the mean squared error is 0.00068, but the test set mean squared error is almost 1,000 times higher, so 0.55. So a very severe case of overfitting. And these high variance gradients and overfitting, this is caused by the type of data that we're dealing with in our research project, namely high dimensional but low sample size data. So my approach is to adjust the LSTM for this type of data. I think what motivates this research is also to narrow the gap between scientific research, which mostly focus on big sample size data, whereas in the industry application, we are facing small sample size data. So all the research paper we have kind of like in these papers, we have kind of like established a common knowledge that neural networks require large sample size data. And only a few papers look at what happens if we apply neural networks to small sample size data. And the same holds true for feature selection. So for practitioners, it's one of the key challenges to identify the best features. And this is because when you have a really good subset of features, then your focused accuracy can improve tremendously. But again, it's only the focus of a few papers. So, I mean, there are a few papers, as I mentioned, so let's have a look at the existing approaches out there. For neural networks and small sample size data, there's the work of Liu et al. In 2017. They have a paper, it's called Deep Neural Networks for High Dimensional Low Sample Size Data. So what they do is they take a subset of these features and put it into a multi-layer perceptron, and they also use multiple dropouts. And then they repeat this times and times. And in the end, they average the weights that they get over this multiple subsets of features and trainings of the MLP. However, there are some shortcomings to this approach. In my work, I also want to optimize the hyperparameters simultaneously. And Liu et al., they don't take into consideration the optimization of the hyperparameters. And also, this approach has only been tested for a simple multi-layer perceptron and for no other neural network architecture. So there's also an approach that takes into account the hyperparameter optimization. This is work that's done by Sandro and David in 2019. The paper is called Unified Feature Selection and Hyperparameter Bayesian Optimization for Machine Learning-Based Regression. So they're also facing a regression problem, and their approach is an end-to-end optimization for both the hyperparameters and the feature selection. So how do they optimize the features? They use a distance correlation threshold. So what does it mean in detail? Let's have a look at this picture here on the right. So they have a data set, and they want to find the best subset of features to train their multi-layer perceptron and to get the best results for their regression task. And to find the best set of features and hyperparameters, they're using Bayesian optimization. I don't want to go into too much detail what Bayesian optimization does due to the time constraint, but in a nutshell, Bayesian optimization is not only randomly guessing a set of parameters that they want to test, like the random search or the grid search, but they have sophisticated guesses. Let me call it like that. Bayesian optimization is initialized with random runs of parameters that are tested on this specific neural net with the features as well. And then the Bayesian optimization takes looks at all these random runs and sees, okay, there's like this area where of the parameters where it's working kind of well. Okay, and we have some prior distributions of the parameters. Okay, so maybe we should have a look at this set of parameters next. And then this set is tested. Then the information of the is taken into account again and used in the next step. So as we can see here, it is an iterative process and it is stopped until some convergence criterion is met. And usually there's only the hyperparameter tuning included in the Bayesian optimization. And in their work, Sandro and David also tune this distance correlation threshold. This is because they want to optimize the features as well. So if a single feature has a higher distance correlation with the target than the threshold, then it is included. And if it has a lower threshold, then it is dropped from the feature set that is fed into the MLP. And by doing that, this threshold can be tested and narrowed down to like a near optimal area by this Bayesian optimization. But there is also some kind of problems with this approach when it comes to low sample size data, because the authors also state in their paper that this approach is only suitable for larger data sets. Why? This is because the distance correlation threshold is only reliable when we have hundreds of observations. And in our research project, we don't have that. And also, the threshold represents a generalization for features in a way that we only look at the individual distance correlation of a feature to the target, but we don't know what happens if we interact, let's say, a feature A and B that are individually highly correlated with the target, but we don't know what happens if we both put them in the MLP and then let them interact. So this is not clear in this approach. And this is where my approach steps in. This is the Bayesian optimization with feature selection and hyperparameter tuning, or in short, both. And this is a term I will use from now on. So let's have a look at the picture. This is pretty similar to the approach that we've seen before, but there's one major difference, namely I don't use the threshold, but I look at every feature individually and I assign a 0 to the feature if it should not be included in the subset, and the 1 if it should be included. So just think of the 0, 1 for each feature as another additional parameter that needs to be tuned. And I also use the Bayesian optimization approach. So this Bayesian optimization then includes some features. I have a look at how this feature subsample is performing, and then adjust the 0 and the 1s for each feature individually until we come to a very good subset of features. One similarity to the approach of Sandro and David is that I also tune the hyperparameters. For example, I also tune the number of layers, the number of units, the activation functions, and also the recurrent dropout, and so on and so forth. So let's sum up the main ideas of this BOP approach. Each feature is separately optimized by assigning a 0 or 1 in the Bayesian optimization. And therefore, this approach is also suitable for small sample size data. And again, it is not based on a generalizing measure, so we look at each feature individually. Now, this is the theory part. Let's have a look at whether this BOF approach is also working well on real-world data. So I've already mentioned we are forecasting the revenue for the local public transport company, the BVG in Berlin. And therefore, we have monthly data starting in 2005 until 2019. And the training set contains of the years 2005 to 2018. In total, these are 216 observations, so not too many. And the test data is 2019. And I've plotted the total revenue here on the right. And what we see is we have a clear linear upward trend, and we have some sort of seasonal pattern in the data as well. Let me point out one thing. So here we have 2019, and after 2019, there's a big peak here on the right. This is due to the introduction of some new products and some accounting inconsistency. So let's take into account this, kind of like more unusual high peak when we evaluate the forecast metrics. And also, let's not forget about this linear upward trend. We will come to that later on again. So this is the time series that we want to forecast. And we also have a feature set that contains of 25 features. We've come up with them in collaboration with the expert from the BVG, and there are monthly dummies included, weather features and population features such as the number of pupils, the number of unemployed workers, number of students, number of tourists, and so on and so forth. So a very rich data set. So let's come to the interesting part, the results of this BOF approach. So which are the features that are selected? We have 5 monthly dummies that are selected: January, April, May, September, December. And it is reasonable that these are the dummies that are selected. Why? Because in January and December, a lot of people buy their subscriptions, and also there are some like specific accounting things that go on there. So January and December are very reasonable. And also April and September. Why? Because these are usually the months where the students' tickets are paid. So at the beginning of the semester. What are other features that are included? Days with snow, also reasonable because snow has an effect on the individual mobility. Other features that are included containing population features such as pupils, unemployed workers, students, and tourists. Why does that make sense? Because we have specific tickets for each of this population group. And if the number of students is increasing, then also the sales of student tickets is increasing, and this has also an effect on revenue, so very plausible. One interesting feature that was selected is the fuel price. So we also had discussion with the expert of the BVG, and in their more or less naive forecast, they weren't too sure whether to include the fuel price or consider it. And this model says, yeah, you should consider it. So it's a good feature to look at. That's one interesting result. And the last feature that has been included are public holidays and Sundays. So the number of public holidays and Sundays in a month. This also makes sense because if there are more public holidays and Sundays and people are more hesitant to buy monthly subscriptions, and they rather opt for single tickets, and this has an impact on the revenue as well. Now, I think the most interesting thing out of this analysis is that for the hyperparameters, the optimal model has, or like the tuned model has 0 LSTM layers. So it only has one dense output layer with the linear activation. This is maybe at first sight a bit surprising, but let me jump back to this slide. Here, don't forget, we have this linear upward trend. So it kind of makes sense, or it is justifiable if we only have this linear layer, this one dense layer. And let me point out the last thing, the training of this tuned model here. On the right, you can see the result of the training. It looks much smoother and much more stable than the first picture I've shown you. It's not perfect, so we have this little peak here, but overall much smoother and much more stable. And I think now we are all waiting for the results, the forecasting results. So let me first say a few words to our forecast metrics. It's the MAPE. One is the MAPE per year and the other is the MAPE per month. Why the MAPE? It's because the accountant of the BVG have chosen it because it's interpretable. And the most important metric for our research project is the MAPE per year. Why? Because if we can spot on predict the revenues for the whole year, then the company has more security in planning their investment. So this is the most important metric to us. We also state here the MAPE per month, the monthly, the average monthly percentage error. Yeah. Okay, so and for the MAPE per year, the tuned LSTM that you can find here is really outperforming all the other approaches. So we've checked multiple linear regression, we checked whole winters, standard time series models, ARIMA, ZARIMA, ZARIMAX, and also machine learning models such as random forest and gradient boosting. But the tuned LSTM is really outperforming them. For the MAPE per month, it is performing quite well again, but I need to be honest with you, the ZARIMA is performing a bit better. So the ZARIMA is at 1.85%, and the LSTM at 1.9, but pretty similar. So what can we conclude so far? The BOF has a lot of advantages. It is suitable for small sample size data. It got rid of this generalizing measure, and it optimizes each feature individually. And it has also shown that it can outperform other forecasting methods for high dimensional, low sample size real world data. So what will be next? I think there must be more research on the BOF for large sample size data, and we need to check if it works there as well. We can also include more things to the optimization, for example, whether an attention layer should be added or not. And yeah, I think everybody has to deal with the COVID shock. That there will be another task for our research project, how to include this shock. And a big vision from our research project is to come up with a kind of like an AutoML tool where each model class is tuned. So it is, so the hyperparameters of these models are tuned, and also the features. And then this tool should automatically find the best overall model for our forecasting task. Okay, then thank you very much for your attention. And are there any questions or feedback is also very appreciated.
Thanks, Nikki. Very good timing. I think we have 2 minutes for Q&A. I don't have any questions in the chat at the moment, is there? But Evgeny has just shown his camera. Do you want to ask a question, anyone?
Yeah, hello. Hello, Nikki, great presentation. I was wondering about the beginning slides, the reference paper you were saying about the feature selection. You mentioned there is some sort of distance threshold. Can you please elaborate on this? Because I didn't completely understand like what this threshold represents.
Yeah, definitely, sure. So in this approach of Sandro and David, and they also want to tune the features to find the best subset of features. And they use this distance correlation. So before the analysis, they calculate the distance correlation of each feature individually with the target. And in their Bayesian optimization, they are not only tuning the hyperparameters, but they're also tuning the distance correlation threshold. So for example, let's say the threshold is 0.1. So if an individual feature has like a distance correlation of 0.2, that means that this feature is included. And if a feature has a distance correlation of 0.05, then it means that it's not included in this run. So, and then this is tested. And if the model works fine with the features that have a distance correlation greater than 0.1, then the Bayesian optimization knows, okay, 0.1 was pretty well. Maybe let's try something in the same area. Maybe let's try 0.11 and check that again. And if the model sees, oh, 0.11 is not performing well, okay, if we include only the features that have a distance correlation higher than 0.11, not so good. Maybe let's go back to 0.08 and see if that is working. So this is the approach here. So you have like one measurement for all features.
Yeah, okay, I understood. Thank you.
Thanks. Do you know how they control for non-stationarity? Because I mean, a lot of these feature selection algorithms are developed for stationary data or for classification, and don't often consider that many of these time series explanatory variables are co-integrated.
You mean in the approach of Zander and David in their paper, how they deal with it?
Yes. Or how you dealt with it, because all of this is, as we saw, is highly non-stationary.
Yeah, definitely. So let me jump to maybe this slide here. Yeah, we see that it's not stationary. What we do is we normalize the data and put the normalized data in, and it's working fairly well already here. So we don't need to have to consider how often we have to differentiate the time series. Yeah, so this is the approach, and it's working fairly well.
Yeah, it's just if you have non-stationary population features, for example, then both two time series will be, if they're both integrated of order 1 or n, then of course they will show some spurious correlation, and that can lead to overspecification with simple correlation approaches. But maybe we'll have some more time in the end to discuss things, because the third speaker is missing. Nikki, thanks a lot for an interesting presentation. Forecasting public transport in Germany is certainly a hot topic, and forecasting revenue from it is even a hotter topic in Berlin. So please keep us posted with your research findings at future conferences. Thanks a lot. Having said that, I think if you can stop sharing your screen, that would be appreciated. Then
Yes.
I will start sharing my screen, if you don't mind. And what a surprise, I will also talk about feature selection. I hope you can see my screen. If somebody can give me a thumbs up, then thanks a lot for joining. I want to talk today about aggregate versus individual time series feature selection. I mean, feature selection is one of the most important topics. Oh, that's a lot of thumbs up. Thanks, guys. It's a very important topic in neural network specification for many years, but I feel that there's a massive gap with regard to the discussion of how to do feature selection. If you have many heterogeneous time series, do you take one approach to feature selection and select one set of features for the whole set of time series? In our case, container shipping data, 70,000 time series. Or do you actually individually determine how to do feature selection? Or do you even do a wrapper around feature selection? And as often in our excitement for neural network and machine learning approaches, we often forget that many of these issues have been solved already satisfactorily by econometrics. So that's a bit of the point. So I want to motivate this, first of all, by the data, right? Rather than showing you a methodological innovation, I want to go back to the data and showcase that some of the simple things that have been developed potentially can help already. I want to then talk briefly about the literature in feature selection, first in classification and what they're missing, and then looking at the difference in feature selection and forecasting. And then I'll show you some empirical results of a variety of different things we did. And hopefully I won't bore you to death because it's just a small thing, but it's a pragmatic, simple approach. Container shipping is the context in which we're doing this, right? So we actually started with a data set, and the challenge is container shipping obviously is the backbone of everything, right? If you think about that, the total industry is valued at 12 trillion, and in the last years, the container shipping industry invested 236 billion into new ships, into new vessels. It is an important area, and they have a variety of decision problems that they need to tackle. And the one we're looking at together with one large liner shipping company is forecasting container imbalances. Most of the container traffic flows from Asia into Europe, and therefore we need to have, if you want to ship the next container from Asia to Europe, you need to have an empty container in Asia. How do you get all these empty containers to Asia? When do you need them? How much do you need them? Obviously, there's Chinese New Year, there's Christmas in the Western Hemisphere. So this has all sorts of aspects that you need to consider. And a lot of the time, vessels are driving from one port to another port, carrying empty containers just to repositioning them. And each vessel is very expensive per day, right? If you're thinking about, hiring a super yacht off the coast of Nizza or Croatia, then that's nothing in comparison to what a small container vessel will cost you. So imbalances are an important thing. We need to rebalance these containers, and that's what we need to do. So accurate forecasting is important, and we want to reduce the empty sailings of expensive vessels and maybe we want to reduce costs, maybe we want to reduce emissions, depends on how you want to spin this. Just a quick thing, the stylized facts of the problem of container shipments, right? This is a time series of actual container shipments with a centered moving average, just showing you the non-stationarity seniority, right? So we have trends in there. We have structural breaks. We have seasonality in there normally when you look at refund containers. We have level shifts, outliers. In addition, we have repetitive calendar effects, which actually show us disruptions. Chinese New Year is important. Christmas, Gregorian New Year, a variety of things. If you're not forecasting China, but you're actually forecasting Japan, then the Japanese bank holidays are more important than the Chinese ones. And so you have a variety of different things. Exports vary from imports, and all these time series vary by regions. So it is an important problem where different features have to be considered in order to forecast a time series accurately between Asia, within Asia, and between Asia, Europe, North America, and so forth. And the second problem is that there's not just a single time series we have to forecast, but we actually have to forecast 75,000 weekly time series 3 times a week. So you can see that there's a scaling issue as well, right? There's, because it's not just one container type, there's many different container types. There's a geographical hierarchy that we have to consider. So we need to consider different features per time series. And the volume really requires full automation, as Nikki mentioned, for AutoML, Auto AI. So it requires fully automatic feature creation and selection. That's one of the challenges we face. Jumping into the literature, of course, we all know that in most data science projects, feature engineering, i.e., hypothesizing, implementing, computing features, and then selecting features takes the majority of the time. A few of the speakers at the conference have already alluded to that, right? You're looking at simple features. Yesterday, the session by SAS saying, the actual magic comes from feature engineering. Looking at the Siemens presentation, I think Georg is in the audience as well, where, miraculously you end up with 22 relevant features in order to do raw materials forecasting, when people have written books about identifying the relevant features for aluminum prices and so forth. So a really, really important but often underestimated aspect in machine learning, at least when it comes to methodologies, systematic methodologies. Right? If you do go to the Web of Science, you have over 14,000 papers with feature selection in the title, and there's, as we all know, there's an increasing attention on AutoML to automate feature selection and feature creation. Just a brief landscape, right? This is basically a screenshot from Budvinik that just came out a week ago on KD Nuggets that tries to explain feature selection to practitioners. This is not a research topic. This is full force applied in this general domain of applied AI and ML out there. That's my point, right? It's not a taxonomy that has been out there. And of course, we always differentiate on the left-hand side, supervised versus unsupervised feature selection. We normally differentiate between filters, which constrain the search space, and wrappers, where you basically compute lots of methods and then try to assess and pick the best one in retrospect using, exhaustive, recursive, forward, backward feature selection. And of course, filters, if you're talking about runtime, filters are much more elegant. You try to, for example, as we saw before, try to identify correlations, limit the search space, and then identify relevant variables by something as correlation or mutual information, core entropy, and so forth, in order to include only those and therefore limit this. And some people actually have hybrid methods or embedded methods, right? The objective of feature selection is, of course, to develop simpler models, therefore shortening training times, avoiding the curse of dimensionality and reducing overfitting. We have talked about that for the better part of 40 years now in neural network research. So this is done. It's well studied in data science. It's well studied in forecasting as well, only under a different name. We often have been talking about variable selection or lag selection. And maybe just to allow that to show that the difference between classical feature selection is when you normally have features F1 to Fi and you have instances R1 to N, then you normally try to identify features, and it's normally a type of aggregate feature selection. You would not determine by each instance, like each customer purchasing a particular order and classification, you wouldn't determine optimal features to predict this instance. You would normally do feature selection and find aggregate features for the whole data set. Some people do subpopulation modeling, and then indeed you have something like individual feature selection for subpopulations, but you would then have to build in additional features and code the instances accordingly. In time series, it is a tad more complicated. We also have features, but we also have the dependent variable itself, YT, of which, of course, we have autoregressive historical lags that we can consider. And for all the features, you also have to determine the lag structure. So for one instance, for one time series, to predict the future realizations, we actually have to look at historically lagged features, contemporary features, or leading features. And that, of course, means you can have one aggregate feature selection for all the time series in a data set, or indeed you can even go as far as doing individual feature selection for each time series to include different variables, different features, different leads, different lags, and do all this fully automatically. I don't want to say that this is of course well known, but there is a significantly increased complexity in temporal time series features, because in time series all the autoregressive lags often are correlated amongst each other. So we have multi-collinearity or multi-co-nonlinearity, however you want to call it in a nonlinear context. But these, you cannot ignore some of the evidence we have seen. And fortunately, therefore, we can stand on the shoulders of giants, because this has been looked at by econometricians and statisticians for the better part of 50 years. So in forecasting, and let me just limit this rather than give you the feature selection for forecasting talk, there's very limited research on feature selection for neural network forecasting. That's what I'm interested in, right? Actually, of the 7,500 neural network papers, 44 look at feature selection explicitly, right? So I think we can say this is under-researched. And that goes in hand, that goes in line with what Hand has said, that most of the research is preoccupied with algorithms and architectures, but not pre-processing, and Files found something similar in 2008. Although input feature selection was identified as one of the most important issues in earlier studies, there still is no widely accepted methodology how to do that. And most people coming to neural network forecasting these days come from the computer science world or data science world, and they employ things that they know from computer science. But I think of the 44 papers I found, 27 basically look at some simple feature selection, like maximum embedding dimension, or ranking based on the imports from random forest, or so there's a few literature on node pruning, input variable pruning, optimal brain damage, something people did when they had smaller computers, and sensitivity analysis. I know that Siemens has an excellent approach on sensitivity analysis. I think they've published some while back, and it's often paired with feature engineering, but a lot of this research stems from finance. At the same time, these are all wrappers. At the same time, there's very limited evidence on filters. Right. I think many years ago with Nikos, we looked at autocorrelation, partial autocorrelation functions, stepwise selection with autocorrelation function on high dimensional data. But there are many established approaches that really are ignored to this day, right? If you just think about one of my favorite methodologies, PC-GETS by Henry and Krolczyk, Autometrics by Dornick, right? Castle and Henry have written a lot about automatic and semi-automatic nonlinear feature selection. There's a massive amount of evidence out there in the econometrics world. We can also look at core entropy and lasso and other things, but we have 40 years of ignored research potentially to go through. So I think there's also quite a few poor approaches. I'm sorry to say that, Nikki, but there's a lot of ML blogs and also commercial software packages that simply use correlation, right? We didn't talk about your paper before, but a simple correlation will lead to including spurious lags, because all non-stationary time series will show some level of correlation unless you actually account for co-integration. We don't have to mention the Nobel Prize of Clive Granger that actually talks about that, right? So I had 3 research questions. Can we employ simple statistical filters like stepwise regression and others for multivariate feature selection? And is a single aggregate feature selection sufficient, or do I need to actually vary the feature selection by time series? And the third question, can I maybe combine multiple feature selections into hybrid wrappers, because most of the time we build ensembles? So, and that's what it is. Just a brief recap, I'm running out of time here. So that's what I presented last year, right? Feature engineering, we can easily create features. I don't mean features per time series for meta learning, what we traditionally have presented here, but simple basic feature engineering. But there's a lot more features that we can generate from, if you understand statistical test, seasonal diagrams, and so forth, right? Not technical indicators. But if you look at that decomposition, calendar event, sine, cosine, right, statistical test, you can then normally take these and transform them in a meaningful way. Square root, cube, box, cox, sax is an interesting way. There's a lot of discussion about talking about similarity in time series clustering. Even Keogh comes to mind, and UC Riverside. What we normally create something called a bag of features, where we permutate all of these, and we have potentially hundreds of relevant exogenous variables. And so that really requires feature selection and feature creation first. And that's our experimental design. We only limit this to 36 regional export time series. These are for the larger repositionings between Europe and Asia. It's still relevant. We have a number of 15 years of data. So we have weekly data, and we try to evaluate no feature selection, aggregate feature selection with filters, stepwise regression. In essence, if there are different versions of that, individual selection per time series with stepwise selection on or a wrapper across this. And then, of course, we compare it to some statistical methods. We also compared against other machine learning methods, and I was pleased to see, Nikki, that you also showed that XGBoost and some of these algorithms that simply cannot handle correlation do very poorly on most time series data sets with non-stationarities, right? Rolling origin, it's a rolling origin, fixed horizon, right? 43 trace errors, everything's averaged. We also report SMAPE, but the results are consistent for MACE and geometric mean relative absolute error. I'm going to jump over the neural network architecture. It's a simple one, so Georg is going to grill me on that one later on, right? It's but it's the same stuff: ensembles, random weight initializations, and so forth, just so that you can replicate this stuff. So, what are our findings? I'm giving you a massive table just to give you the relative ranking of stuff, right? And the first thing that comes to mind, I'm just showing you the current thing that this is a benchmark model we built over 10 years ago. So we are in production with neural network forecasting ensembles for over 10 years, weekly, 200,000 forecast run routinely around the world. So these are the benchmark methods. That's the one in purple. And then the benchmark methods are below. You can see that all of this is ranked. So we have the name of the algorithm, and then we have forecast errors and ranks of the forecast errors. I'm showing you the mean SMAPE, the median SMAPE, the weighted MAPE, volume weighted MAPE, also important for the business, and then the ranks by that. And you can see they're sorted by mean SMAPE. So unfortunately, all our univariate statistical models are towards the end of it. That's good. I mean, it means that we're not completely in the wrong path when it comes to neural networks. If we then calculate univariate neural networks, univariate multi-layer perceptrons with and without model selection, right, or feature selection, they will also range towards the end. I mean, they don't have any causal information, they don't have exogenous information, but they outperform, on average, they outperform the statistical benchmarks. And we find that again and again, that neural networks are fairly robust and accurate. Just denoted with a star is always if you actually do individual feature selection, across multiple feature selections, right? So that's a star, and you can see that this normally comes out at top. So just using one input feature set or another input feature set, aggregate across all of the time series does not work. You actually have to do feature selection for across multiple feature selection approaches for a data set. The next section then we have is actually, we have multivariate models, which then come next, right? Intuitively, if we add explanatory variables, we find the same thing, but the relative ranking is still the same. The multi-layer perceptrons with features with individual multi-layer, but the selection over three feature sets actually outperforms the other ones. But now comes the important part, that we actually do different types of statistical feature selection, and you can see that they actually don't outperform the purple benchmark, which is the one of an expert that who's built the lags. That expert would be me 10 years ago, right? So unfortunately, based on these simple lags, we cannot outperform something that somebody with the econometrics knowledge of looking at autocorrelation, partial autocorrelation, and so forth has developed. But it gets remarkably close with zero time, right? Even something as simple as stepwise. Again, you know, the hybrid wrapper of selecting across multiple feature selection techniques outperforms each individual one, although just marginally so. It does have longer runtime. It has to calculate all the feature selection approaches, but that's there. And then what we do is then we add in the additional bag of features that I've shown you before, and that really drastically improves everything, which normally means you have a lot larger runtime, and you cannot really coordinate this anymore automatically, manually by a human expert. But indeed, now you can find that multivariate neural networks, multi-layer perceptrons, with multiple feature selection approaches, selecting the best feature selection approach for each time series really outperforms all the other approaches, and quite significantly so. Right, so well, that's fairly straightforward. I can also give you the runtime, because that's important as well. We talked about parsimonious things, and the runtime drastically reduces, right? So it's a 13-fold reduction of runtimes over a large set of model lags and features that were created by human experts. In fact, 4 seconds to 59 seconds means we can run a lot more algorithms. But if you want to take the best approach, you actually want to build a wrapper around multiple filters, well, then of course you buy in additional runtime, which is in this case 5-fold. So it means you can run a lot less experiments. Just some of the forecasts, with regard to that, just to show you the level of detail in which these features are automatically picked. But I'm running out of time, and this just rolls out of time, and you can see how that's forecasted. We, of course, do residual analysis. All of this is well behaved. What does it mean from a business point of view, right? That's often the question. Well, we know what the difference is to the benchmark method they've been employing, and in fact, it is roughly 20%. It's roughly 100 TU, 20 foot equivalent units of containers every relation every week, which we know that the largest vessel carries roughly 1 billion in cargo. So if that drives empty, you're not transporting 1 billion dollars in cargo. We know there's one sailing every 44, that takes 44 days. So roughly at the very end, you can see the runtime of a forecast improvement we've seen, apart from the improvement in runtime, but the accuracy is roughly $10 million a year. And that brings me to a summary. Multivariate MLPs outperform univariate statistics. I think that's a given by now. For some people, they still doubt this, but individual feature selection improves forecast accuracy over aggregate feature selection. Forward selection normally outperforms backward. There are many others to be investigated, and stepwise normally outperforms non-stepwise approaches. And MLPs with extended features outperform those with less features, but they definitely require feature selection. And the runtime is, of course, affected. And so the next steps for us will be to expand this, look at econometric contenders. PC-GETS and Autometrics are really quite good. Autobox also. Lasso is a standard one, but initial results weren't promising. And then maybe also just include Random Forest XGBoost, just to show that these relevance ranking that they normally achieve do not really help you if you have correlated features that are non-stationary. So that's it. That's ICAST. We also created a small spin-off where we basically play around with things like this, which are close to research, but actually are in practice, are valued in practice. And that brings me to the end. I think almost just in time, maybe a little bit over time. But are there any questions?
No comment.
Hi, Georg. I can recognize your voice. So please.
Do you allow me to say something?
Yeah, I think so. I think the time is up, unfortunately. We started a little bit fashionably late, but we can probably take some time. The final speaker, if you're joining for the final speaker, it's unfortunately not here. So if I would like to close the session in a minute, but then we can take Q&A for those of you that want to stay in. Nobody will be mad if you leave now to join other sessions. But otherwise, I mean, we have Nikki here as well, and then maybe we can use the remaining 20 minutes for some Q&A. All right, Georg, please. But the session is officially closed otherwise.
Okay. So especially in the second paper, the temporal structure is important, which means the memory in the system is important to do the forecasting. And if you have such a thing, why are you still sitting on this feed-forward neural networks instead of recurrent neural networks?
Well, it's a good question. I mean, we also try recurrent neural networks. We also try some of the more state-of-the-art algorithms, which we seem to be very much struggling trying to get a handle on, right? A lot of the time, so if you're comparing it to your historically consistent neural networks, right, we don't really have a lot of explanatory variables we have to predict simultaneously, right? We have bank holidays, we have vessel capacities, we have a variety of other things that are endogenous. So I don't need to, it's not a vector autoregressive issue. I don't need to predict these into the future. They are often known. So that makes our life a lot easier, and we are aiming for simplicity. Having said that, I have not tried historically consistent neural networks. The Python package that you just released might be helpful for that. But for the other reasons is that we haven't really found a lot of evidence on moving average processes that would help in building this in an effective way, right? So we actually looked at specifying Aremax models with moving averages, and in particular with the intervention variables, we weren't able to handle these very well because they're really, spike disruptions. But it's a good point. I could try out other things as well. At the moment, this seems to still outperform other things. But maybe we can do a head-to-head. Yeah.
Yes.
But for me, I always start with a simple algorithm rather than looking at the problem and the world, of course, with all its variables and time evolving. Do I need to capture that complexity in something that I have to forecast 250,000 times fully automatically every week? Maybe I don't. Maybe I can take a shortcut. And for model maintenance and other reasons, transparency, we are at the moment still very much in bed with this algorithm, with this very, very old and very, very simple approach, which still outperforms most statistical approaches. I mean, maybe we'll do this more as a dialogue. Nikki, why did you choose LSTM? Is a particular motivation that you evaluated against? Did you do some pre-testing against MLPs and or I don't know other network topologies and found that this actually works the best, or is it just the choice that everybody makes at the moment?
It's for one part, it's kind of because everybody's going with recurrent neural networks, and also it's based on my experience so far that I've seen that RNNs work as a for my projects have been working better, and then I was like, okay, I had good luck with them. Let's try it again. I haven't tested MLP so far for the revenue forecast. And one thing I wanted to mention, I didn't differentiate the revenue time series, but the other population time series. So there's only the difference. I only took the difference, but for students and pupils, it's still only increasing in Berlin. So we still have this upward trend, even in the difference time series. The first difference, yeah.
I think even if you look at more modern architectures, right? If you have any sigmoid function in your activation layer, in your hidden layers, or in the output layers, then you always get into saturation effects when you have linear or nonlinear trends. I mean, it's a built-in problem, but you can decompose the problem. You can maybe feed in an explanatory variable or so. But my experience in differencing is that you're then building stuff on differences, which makes things very, very volatile indeed. But that's that. I think there was a question to all. I'm not sure if that's related to my talk or Nikki, your talk as well. Did you test any fancy deep learning structures like transformers?
For my part, I can say no, I haven't done that.
Neither have I. I think today. I think at the moment we're challenged that we have almost as many neural network architectures as we have data points. Right. So now we don't, no longer do we have and we have unlimited architectures for each of these, unlimited topologies for all of these architectures. So it's basically a real challenge to navigate this. I think irrespective of what you do, feature selection will improve. Right. I think if you don't generate intelligent features, you will always struggle irrespective of what you're trying to do. And you may hope that you're generating, a really intelligent feature pre-processing in your network topology that can automatically extract certain features, like, I don't know, velocity, curvature, whatever it is you think is relevant. But most of the time, these algorithms will struggle. I mean, most of the deep learning architectures were developed with a particular task at hand, and it wasn't time series prediction. So I think the structures are not well aligned with what econometricians were traditionally trying to build into models. Having said that, I'm not an econometrician. Maybe it is just that what the econometricians do. But yes, indeed, it's also one of the challenges there.
I would have a comment on this with the transformers and so on. To think about transformers means that you look for similar regions in the past that you see in the moment, which means, so this is a little bit like clustering a time series and then speaking about only of the clusters. But this is a phenomenological approach to working with the data. If you want to develop a causal model which describes the development of what's going on there, then you need something which is describing causality inside of this. And this is completely different to say, I only want to speak about numbers, and I do not have this internal structure of time in the numbers. And so, That's the one point. The other point is you all are interested in the feature selection, not in the general model building. And so therefore, I would say if you have so many features there, sometimes it's a very good idea to build an inverse model. See, you have many inputs, and then you have several outputs that you want to explain. And then you hustle around with how many of these inputs are really needed to explain the output. So build another network where what you normally have as inputs are your outputs then, and what you normally have as outputs are your inputs then. And then you turn around the time direction, and then you try to test it. And then you see which one of the many variables which you normally use as features have an interrelationship with the target variable which you are normally interested in. And then I simply would take let us say I would have 20, 30, 40 of these feature variables. And then I would check which one of the feature variables really have an interrelationship to the target variables I'm interested in. And then I would take the best of them and the rest in the trash box.
That sounds like a great idea. The only downside is that I have 75,000 time series, Georg. So I will send my 75,000 time series to you and you can do this. But I'm a big fan of the way you're doing sensitivity analysis as well, right? Looking for nonlinearity, changes over time, really sophisticated. But it's just so computationally heavy that that if I do this, to automate this is really tricky. Having said that, we normally don't rebuild and estimate or re-estimate all the model parameters for all time series every single time. So we can fix them.
This is something I understand, but in the moment I speak only about the general building of the framework. Is whatever, for example, DAX, Dow Jones, also an interesting additional variable in the model building there. And so there you could say, I have so many ideas, and if I drink some beer, then I will have more ideas. So which means the length of the feature selection vector on the input side could be boring length, could be boring much. And so therefore, to figure out of very many input variables a reasonable subset. This is better in an inverse model than in the forward model.
I think this is a great idea. I know that you at Siemens, you've worked on a lot of forecasting a lot of data sets with few but very important variables like electricity prices you presented before, copper, aluminum prices. Obviously, if you crack one of these problems, you can get filthy rich, or you help the Deutsche Bahn or whoever, but if you can do this, then obviously there are different things where identifying the right variables is very important. But I think you're right. There's just a lot of methodologies that are, maybe that's my point on the paper, simple methodologies or more complex methodologies that are being ignored for the sake of going for relative variable importance in a random forest or something like that, which you can easily extract from an R or Python package. But I think there's a lot more. And so hopefully we'll be able to bring this a little bit together, right? This confluence. But I like this idea of inverse models as well. Maybe that's something we can look at. I know that Georg has, for those of you that don't know, Georg Zimmermann, Fraunhofer, formerly Siemens senior research principal for neural networks, I think.
30 years.
And for 30 years, and he gave I don't know, 15 or 20 tutorials at the previous ISF conferences when these were still held in person. So I know that he has a slide deck which would probably allow us to dig into this topic for the next 8 or 10 hours and then move on to the next 20 topics that he also has prepared. So Georg, we still have to organize this workshop at some point. But we cannot do it online. So once we're back in the physical world, because you're right, we need beer in between to keep us fueled.
Yeah.
Very good. Any final questions from anyone else? I don't see something.
Yeah, I wanted to ask about you mentioned the problem of this cross linearity, so between the variables. So how did you solve that in your approach? Did you look for the correlation between variables as well? Or?
Well, it depends if you have multicollinearity, right? If you have a non-stationary variable and you have another non-stationary variable. All I'm saying is that if you have one time series that's trending and another time series that's trending up or down or anywhere, you will automatically have a significant correlation between the two. And that is a particular problem. If you have bank holidays, if you have dummies for quarterly data, it's not a problem. But if you have population growth and you have revenue growth and you have retirement age growth and or general income declining, this will automatically tell you, if you use correlation, that all of these features are meaningful, irrespective of how high or how low you set the threshold. And you will no longer be able to rank these things. And then the question is, you have seasonality that you have to control for, and then you have disruptions as well, talking about politics in Berlin. So I think, it's very easy to get fooled by looking at a simple measure, trying to or overlooking what the assumptions behind that measure are, whether it's a rank-based correlation or Pearson correlation or a dynamic threshold or statistical significance. This will never work for time series. Right? This
One last warning. Do not think too fast about correlation measurements. Correlation is a linear structure. So if you use this to filter something out, you automatically have a bias in the direction of linear models. And this is a waste of effort for all the rest of it.
Yeah, you could look for core entropy or other more robust metrics, for example. But indeed, I think a better approach is to include, look at David Henry, PC-GETS, right? He's written a lot about this stuff, or autometrics, and see, how think about including lots of variables and then doing sensitivity analysis potentially, right? Checking for nonlinearity. And also measuring this, errors. What if an error, in our example, there's a few more tricks to be considered. Forecasting around 2 or 3 weeks in the year will drive all of the profit that you can derive, and that's Chinese New Year. But on an average error measure, this will just be 1 or 2/53rd in all the average of the error. Right? So if you're not careful, you can predict all the uninteresting periods of a time series really well, but then when you're trying to forecast, the Christmas peak in public transport or the back to school peak in public transport, then you're terrible, and it makes the model unusable. So there's lots more stuff to be said, but I think non-stationarity, co-integration, Clive Granger, right, Nobel Prize on co-integration. Basically, the reason why people in finance up until the 80s thought they would get filthy rich because everything was related. Oh, they found correlation, but then they couldn't predict anything. Right? Halbert White's first neural network paper, 1998, on IBM stock returns, right, is a good example of how he showed that he can crack the stock market, and he later on I think he realized he couldn't, although he is a very famous professor now.
And the models you're running, are they trained in are they local models? Are they trained in a series by series fashion?
Yes.
Or? Okay. So maybe that's my comment on recurrent neural networks. So if there is if there's a lot of homogeneous time series, that's something that recurrent neural networks are most successful with like cross learning and cross validation.
Yeah, of course, global models, pooling, subcluster population pooling and whatnot, are all things we can explore. Just the 20 minutes are too short to present everything. But I thought, thank you very much for an engaging discussion. It was almost like a mini panel. Thanks, Nikki, for your nice presentation. Thank you, Georg, for contributing. Evgeny, thank you very much also for contributing. The others, thank you for being there and staying quiet, more or less, without any questions. Enjoy the conference. We are spot on time. And I look forward to seeing you at the next sessions.
Thank you.